On this video, I will present a revision of some basic concepts related to the module. Today's lecture is about waves, electromagnetic spectrum, oscillators, wave resonance, harmonic waves, and wave superposition. There are many different manifestations of a wave in the nature. A wave can have mechanical properties and it propagates through solids or fluids. The water wave, the sound we hear, or an earthquake are examples of mechanical waves. Remember, it does not propagate on the vacuum of space. Electromagnetic waves is the other wave manifestation. It occupies the electromagnetic spectrum and propagates through waveguides and also through the free space of air or vacuum. The curious is both mechanical and electromagnetic waves behaves in a very similar way and allow us to do some analogy. Also, we cannot forget to mention about the gravitational waves that propagates to the fabric of space and time. And the recent LIGO experiment proved the existence of such waves. A sine wave is well known among us, and this is the main object of our analog communication studies. The wave parameters are the period, that's the one wave cycle, the frequency, that's the number of cycles in 1 second, the amplitude, the wave speed, and the wavelength. The wave speed depends on the nature of the wave and the media where it is propagating. For instance, the sound wave in the air propagates at 340 meters per second, and solids, the speed is usually higher. The electromagnetic waves propagates at free space next to the speed of light, that is around 300,000 kilometers per second. However, the propagation speed on waveguides and cables is usually less than the speed of light. The electromagnetic spectrum is a frequency range starting on oscillating waves above 0 Hz up to extremely high frequencies on the order of gigahertz and beyond. The audio frequency range occupies the spectrum from 10 Hz up to 20 kHz. The frequencies between 500 kHz and 1.5 MHz is the part of spectrum where we have the broadcast of the AM radio stations. From 2 MHz up to 40 MHz, we have many different services dedicated as the radio amateur band. Frequencies above 45 MHz up to 70 MHz, we find the analog television channels or VHF channels and the UHF channels that is between 180 up to 215 MHz. The FM radio station is between 88 MHz up to 108 MHz. Mobile phones operates between 800 MHz and 3.5 GHz. Going above on the spectrum, we find the visible light that is also represented on the electromagnetic spectrum with frequencies between 430 terahertz up to 750 terahertz. Question. We have a sine wave of 1 kilohertz. How is the period of the wave? The period is 1 over frequency. So 1 over 1000 Hz is 1 millisecond. 1 millisecond is 1 wave cycle. We have a carrier wave of 100 MHz. Calculate the wavelength. The wavelength is the velocity of that wave over frequency. So we have the wavelength equals to the speed of light divided by 100 MHz, what gives 3 meters. The wavelength of 3 meters means that the ideal size of the antenna of our receiver is 3 meters. However, we can reduce the size for 1/4 of wavelength or 1/8 of wavelength. Almost all the objects around us can oscillate when one external force acts on it. Some material, as the metal tuning fork or the crystal tuning fork, has a sharp resonance frequency and it can oscillate at the maximum frequency amplitude in its fundamental tone. The quartz crystal, due to its piezoelectric properties, can be used as a component to generate a source of oscillation. The mechanical resonance of the vibrating crystal can be used to create a constant electrical signal of the same frequency. The crystal can also be used as an audio transducer and can perform as a microphone or a speaker. Remember, the speaker with a permanent magnet and a wire winding is also a transducer that converts electrical waves to mechanical waves. The microphone transforms mechanical waves to electrical ones. According to Cambridge Dictionary, resonance is the production of a sound as a result of a vibration of another object. The same principle applies also to the electromagnetic waves. For instance, when we have two identical tuning forks near each other and one of them is beaten with one object, the other tuning fork will also vibrate without direct interference. The opera singer, in theory, would be able to break a crystal glass using the same principle. For the electromagnetic waves, one antenna will resonate at frequency corresponding to its length. Harmonic waves. Harmonic waves is a signal that is the integral multiple of one source of oscillation. One ideal oscillation source would emit a single tone on its first harmonic, but in reality, when you play a tuning fork or a guitar string, for example, it does emit more than one tone. The object will also vibrate at the double of the fundamental frequency, and the triple, and the quadruple, and so on. However, the consecutive harmonics will have less amplitude. The purpose of this slide is to display the waveform and frequency spectrum of different oscillation sources. A tuning fork is the one showing the most perfect oscillation. Looking at the time domain, you can see one constant and repetitive wave cycle, and on the frequency domain, you see the spike correspondent to its resonating frequency. The flute and the violin emits a range of harmonics with a high amplitude, and this is the instrument footprint, or timbre. The human voice usually does not reach more than 5 kHz of bandwidth. Superposition of waves. The superposition of waves occurs when two waves cross at a point. The result is the interference between each other that causes the change of pattern of those waves. The interference can be constructive or destructive. A constructive interference, it adds together, getting a wave with higher amplitude. A destructive interference, it adds together or subtract each other and results of the cancellation of that wave. On this slide, we have some animation of the wave superposition. The wave on blue and red is the primary waves, and the black is the resultant wave. On the left side, we have two waves with different frequencies. And these waves interfere each other, causing a resultant wave with one uneven pattern. On the right side, we have two waves with the same frequency, but the phase is constantly shifting, causing an interference on each other, and the result of this interference, it is one sine wave going off on sine wave with the same frequency, but the amplitude changing from 0 to its maximum amplitude. And here is the end for today. I hope you enjoyed the video, and if you have any comment or any question, please contact me. Thank you.